Good evening, YouTube, and we're back. I think what we're going to do today is going to redo our 2017 Pythonic Calculus Executive Summary. The last screencast was a little bit long, so I think we're going to try it again, make it a little bit shorter. So how about we create a file name. Let's try this. 2017 Calculus. Pythonic Calculus Executive Summary. Take 2. Aha. And we're going to make this a Jupyter notebook, so we'll do Python. Let's just practice with Python. Here we go. Alright, so in the first cell, I'm going to reorganize this a little bit. We had an issue with how to import stuff and whatnot last time. I'm going to try and do all my imports right here in the first cell, sort of like an initialization cell, so that if I come back to this, say, tomorrow, after I save the file, and I have to run some code later on that depends on matplotlib or numpy, whatever, all I have to do is rerun this first cell. I'll call it cell 0 or step 0. And the cell in question if there's a dependency issue due to markdown. And so let's do that. So let's start with a little comment. I always start with a little note to self. My name, the date, and what are we up to now? Today's July 9th. And what we're doing, Pythonic Calculus Executive Summary, take 2. I don't usually do 2 takes. I don't usually even edit my videos, but there you go. Alright, so I'm going to call this step 0. Sort of like initialization stuff. Okay, so here we go. And now, recall what we're talking about here. How do we use Python instead of a graphing calculator on the AP exam, on the Calculus AP exam, where you have to be able to find roots of equation numerically, find numerical derivatives, find numerical definite integrals, in other words, numerical definite integrals, and graph in an arbitrary window. So what they don't tell you is that you have to define a function somewhere too, right? So how about the first thing I'm going to do here is define a function I'm going to be using as an example. For example, f of x equals x squared minus 2. Okay, and let's do some imports from matplotlib .pyplot, Pythonic plotting, import all. Okay, and from numpy, import all. Now, what I'm importing here is sine, cosine, pi, a range, linspace, all that kind of stuff that's in numpy. Import everything, and there you go. Okay, so now what I'm going to do here also is I'm going to define the function f of x. Notice the colon, enter, that 4-space tabbing, that's syntactic. We're going to return x squared. Remember, super multiply, use exponentiation instead of the caret, because this is not basic. We're not in CI basic anymore. And so just for fun, what if we print, let's label the output here. How about f of the squirt, oh yeah, numpy also has squirt in it, of 2. Alrighty, and this is just a label. And here's the actual calculation. Space it out a little bit, that's just a string. Let's actually do f of the squirt of 2. And what should you get? Well, let's see. Is that all correct? Well, let's find out. Control Enter. we should get 0, and that's pretty darn close to 0 within round-off tolerance, okay? So let's say the 3 places, 4 places, whatever you like. Because if you plug in square root of 2 into x squared, you're going to get 2 minus 2 is 0. Again, in Sage, it will probably give you 0, but here we get a little round-off error, so that's okay. All right, so there you go. That was step 0. Now, step 1. Now, usually they say, solve an equation and then get numerical derivatives and then get definite integrals and then, plot in an arbitrary window, but I'm going to find roots using Newton's method, which is based on derivatives. So how about we do derivatives first? Here we go. So step 2. Where am I? I'm in the wrong cell. Wrong cell. Okay, comment, step 1. I'm going to do it this way. Okay, in step 1, we're going to find numerical derivatives as limits. So find a numerical derivative as a limit. And how we're going to do that? Well, we're going to define the derivative functions. How about we do define diff, like differentiation, and we're going to let the user input the function that they want, the x value where they want the derivative to be evaluated, because it's a numerical derivative, not the derivative function necessarily. And for whatever value of h you want, make it small. And here you go. And so what I'm going to do is I'm going to do a little convergence table where h is getting smaller and smaller and smaller, and so we get closer and closer to the correct answer, right? Okay, so again, enter, that's that tabbing in there, that's syntactic, don't mess with that. Return. Now let's see the difference quotient, right? So the quantity in the numerator is f of x plus h minus f of x, that quantity all over h. Okay, there you go. Alrighty, so now let's see. Let's print quote f prime at 2 equals, all right, that's just a label, and so let's labeling this convergence table. So how about we do this? How about for x in range 5, so x is really 0, 1, 2, 3, 4, and again this tabbing in is for the loop. Let's print the diff, whoops, of our function f that we defined above, x squared minus 2, at 2, with h getting smaller and smaller and smaller. In other words, 10 to the negative x. And I think that'll do it. So if x is 0, 10 to the negative 0 is really 1. So h is sort of large, and then when x is 1, then 10 to the negative 1 is a 10th, so h is getting smaller, and then when x is 2, 100th, and x is 3, 1,000th, like that. Control Enter, or click the run up here in your Jupyter Notebook, and does that make sense? Let's see, what is the derivative of x squared minus 2? It's 2x, so if I plug in 2, I get 4, and we're getting closer and closer to 4. I think I like that. Alright, a new cell, click it. Alright, in this cell, let's call this step 2. Let's use Newton's method in a limit to find roots, and using the derivative function that we just had a minute ago. So let's see, find roots using Newton's method as a limit. Okay, so find roots using Newton's method as a limit. Okay, and let's see here, let me take a look at my notes here. Good. Alright, so what we're going to do, we're going to define Newton's method. So how about define the root function? Okay, now the root function is going to take the function that we're setting equal to 0. We can find the roots of it at, equal to 0, when it's equal to 0. So if a function is f of x equals x squared minus 2, we're really asking when is x squared minus 2 equal to 0. And a guess near the root that you want. Okay, there you go. And so what is Newton's method? Well, Newton's method, what we do is we're going to return a better guess. Okay, that guess being the current guess minus f at the current guess divided by the derivative, okay, so diff of f at the current guess, and let's fix h to something small, 10 to the negative 6, let's say. Alright, and if that's not good enough, we could always make it smaller. And so let's say, for example, let's find the closest root of f of x equal to 0 near x equals 1. Okay, so how about this? Print, quote, this is just a label, or string, closest root of f of x equal to 0 near, let's say, x equals 1. Now think about it. If f of x is x squared minus 2, it has two roots. X squared minus 2 equals 0 means x squared is 2. So the square root of both sides, x is plus or minus rad 2. So the root closest to x equals 1 is going to be positive rad 2. Let's see if we can get a numerical approximation for that. And here we go. Alright, so let's make a convergence table. First of all, let's set the guess near 1. Okay, that's our initial guess. And then for, whoops, what the heck is that? For x in range, and if it doesn't converge, you know, in range 5, we can make it range 10 or something. Range 5 is pretty good, I guess. And so what am I going to do? I'm going to print the current guess, so it's going to print, the first time it's going to print the 1. But then what I'm going to do is I'm going to let the guess equal the output or the return of the root function we just defined, taking the function that we're setting equal to 0, which is f, and the current guess. And let's run that, control enter. And so the closest root to x equals 1 is, well, that is rad 2, basically, isn't it? Now, I don't have all decimal convergence, but I do have tenths, hundreds, thousands, 10,000s, 100,000s convergence, you know? All right, I mean, I can go crazy and make it, I don't know, 10. And now I got, let's see, tenths place, hundreds place, thousands place, 10,000s place, 100,000s place, millions place, 10 millions place, 100 millions place, billions place, 10 millions place, 100 millions place, billions place, 10 billions place, 100 billions place, trillions place, and well, I guess this place doesn't match. So yeah, that's pretty good. We could make it better, making this smaller even, I guess, if you want. This, I could do the same thing up here. What if I run this for 10? Let's see. And we get closer and closer and closer to 4. This is, yeah, damn close to 4. Okay. Anyway, so you get the idea. All right, let's get another cell. Hover your mouse down here until you hit the blue bar, click it, and you get a new cell. All right, so what's step 3? Well, step 3 is going to be doing Riemann sums to find a definite integral as a limit. Alrighty, so let's see about that. Alright, so last time what we said was, let's see, we're going to comment, note to self, step 3, find the definite integral as a limit. Alright, as n gets larger and larger and larger, the number of Riemann rectangles get skinnier and skinnier and skinnier, and the error goes to 0. Alright, now in class we figured out that we could do this. We could, let's see, let me think about this. Alrighty, so what, for fun, let's see, what if I say print, whoops, range 5. Yeah, that's not what I want. Okay, how about a list comprehension? Print, okay, I'll make a list, I for, whoops, I in range 5, that's what I want. And so that this should be 0, 1, 2, 3, 4, let's say. What'd I do? Oh, what? Sorry, a little syntax error there. And there you go, perfect, okay. So let's say I want 5 rectangles, right? Okay, so let's say we're doing a left Riemann sum. So the 0th rectangle, the 1th, the 2th, the 3th, the 4th, that's not English, I know. And so what we're going to do is going to say, okay, let's take a partition, let's say from A to B, and chop it up into n rectangles. Okay, so what we want to do is something like this. We want to define h, the width of each rectangle, or actually the height of each trapezoid. I'm actually going to do a trap sum eventually. Let's make that b minus a over n. Okay, and so let's define b, a, and n. Let's say, just for the sake of argument, let's say a is 0, and b is let's see, what I'm going to make b. That's for fun, pi. That's from numpy, okay. And n equals 5. And let's put the n here. Control Enter, get the same output. Now, this is what I want, though. I want that to be the x-coordinate of the left side of each left Riemann rectangle. So won't that be a plus I times h? Let's see. Alright, let's make this less crazy. How about from 0 to 2? So think about it. If we integrate x squared minus 2 with respect to x, we get x cubed over 3 minus 2x. And if we do that from 0 to 2, plug in 2, you get 8/3 minus 4. What am I doing? I'm doing something weird. Hang on. Alright, That's hard to see that these are the right partitions, but I think they are. Alright, let's just for the sake of argument. What if I did from 0 to 5? Right, that's it. From 0 to 10. That's what I'm going to do. Yes, that's it. Okay. From 0 to 2. Yes. Okay, yeah, and that's exactly what you want to see. Alright, but I'm going to go something crazy from 0 to pi, okay? There you go. Now what I want, though, is the function value there. Okay, so I'm going to say, what is f of that? F of that, here's your list comprehension. And what's nice about lists is that they're just sequences. And what's nice about sequences is that you can sum them, make a series, and get your Riemann, sums that way, right? Okay, now that's the height of each rectangle. Let's multiply times the width of each rectangle, or the height of the trapezoid. Okay, and then we're going to sum all of that. Let's see, let's sum all of that. Okay, so let's put that whole list in a sum. So if we sum that, alright, so if I go all the way over here, that closes the sum, but it doesn't close the print. See, the green print is closed. And so we're adding all that stuff, and we'll get 1.15, whatever, okay. Okay, that seems to be working. Let's see, what am I doing? Alright, so what I want to do is I want to make that a function. Okay, I'm going to make this a function. I'm going to say the function, let's go here. Let's make this, define the function LSUM. Okay, and LSUM is going to let you define the function you're integrating, and then the limits of integration a and b, and then the number of rectangles you want, right? Okay, in there you're going to have to define h because it's changing, and you're going to do the print thing. Let's see, can I just space this out? Well, actually, it's not a print. What would it be? It would be a return now. So let's get rid of the print. And let's get rid of this parentheses, that's extra. All right, and now how do we test that? Well, let's put that in a convergence table. Okay, so how about 4x in range 5? And again, if 5 isn't good enough, we can play with it. And what we're going to do is going to say, okay, let n equal 10 to the positive x this time, because I want n to get large, right? So 10 to the 0, 10 to the 1, 2, 3, 4, 5, right? Okay. There you go. And let's print. Okay, so what are we going to do? We're going to print the LSUM of f from 0 to pi, oops, in n rectangles. Now let's run that. Now let's see, I don't need this anymore. I don't need this anymore. I don't need this anymore. Alright, so that should be the LSUM. Let's see what that does. And the answer is about 0.0. Okay, very good. Now, alright, so that's good. Alright, there's your LSUM. Now what we want to do is make this better. So I'm going to say, okay, print, let's see, the quote, this is just a label or string, the definite integral of f of x from 0 to pi equals. There you go. Alright, so what we're going to do is going to make it better. What we want to do here is, let's define a right sum. Now, the right sum is the same thing as a left sum, except the left sum uses that 0th rectangle and not the last one. So we're going to get rid of the area of the first rectangle and add the area of the last rectangle for the right sum. Or I could change this and do an I plus 1 here, I suppose, right? We could do that too, I suppose. But all right, so let's just do this way. So let's do our sum of your function. By the way, this idea of putting the function there was clarified by a friend of mine on the EDU-SIG Python forum. Kirby Urner, thank you very much. It's a nice little technique to put the functions you're integrating right there. Very good. Without parsing and whatnot. I had used to do it in a very complicated way with passing strings and parsing and blah, blah, blah. You don't have to do that. Alright, so we're going to do the same thing here. We're going to say h equals the quantity b minus a over n. Alright, but now what we want to return is the LSUM of that same function, whatever function we're talking about, from a to b in n, right, minus the function value at a, that's the height of the first rectangle from the left sum that we don't want, times h, the width, so you get the area, plus the function value at b, which the right sum uses, times h to get the area, and then that would be, I think that would be your right sum. Now, your right sum should converge more or less to the same idea. It may not be the exact same values, but this should test out the same. And more or less it does. 0.53, what's an overestimate? So the left sum here is an underestimate, right? Our sum here is an overestimate. Okay, that's fine. And so what's trap? Well, what I really want to do is trap. So let's put trap here. And what is trap? Trap is simply, let's see, define the function trap of the function we're integrating from a to b in n rectangles. Okay, what is going to be? Well, it's simply, let's see, do I need h here? I don't need h here, do I? Okay, so it's going to return the average of LSUM and right sum. So open parentheses, LSUM of your function from a to b in n plus R sum of your function from a to b in n. That quantity is divided by 2 to get the average. Okay, and I think that's your trap sum. There it is. And run it. And there you go, 0.52214 converges, and again you can do, I don't know, range 10 if you like. Get a better estimate even. and it takes a while because it's running all these functions and stuff. And so we got tens place, hundreds place, thousands place, 10,000s place, 100,000s place, millions place convergence, 10 millions, 100 millions. Oh, it's still going. 100 millions, billions place convergence, 10 billions place convergence, but not the 100 billions place for convergence. Okay, there you go. And it's still running. 1, 2, 3, 4, 5, 6, 7, 8. Ooh, this is taking a while. Well, let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, it shows all 10, right? So 1, 2, 3, 4, 5, 6, 7, 8. It's got 2 more iterations to go. Yeah, that's what I did. Ooh, it stopped. All right, you know, let's just do 5. And it's stuck. What happened? Error. Line 16. Uh-oh. Something got screwed up. See what it... Okay, I gotta run this again. Okay, there's F. Let's run this again. Yeah, see? I told you I needed that initialization step 0 cell. Okay, good. Alright, that's fine. So we got 4.052224 and convergence to the tenths, hundreds, thousands, 10,000, 100,000 place. That's fine. Leave it. Okay. Alright, so what's step 4? Step 4 is graphing in an arbitrary window. Okay. So let's think about this. Alright, so let me show you what we did. Last time we got bogged down with this. We said, okay, here's step, I'm going to call this step 4. Oh, I did that thing again. I don't like that. I don't know why I got that weird kind of cell. Okay, I'm here. Okay, so shift, hashtag, okay, so step 4A. Alright, so plotting in function mode. Plotting in function mode. Alrighty. So last time what we did was, we did this. This is all commentary because I'm not going to do it this way. We did import numpy as np. And then we did import matplotlib.pyplot as plt, or whatever you want to call it. So it's just not some other reserved word or variable you're doing already. And then I did something like this. It said let x equal np.linspace from 0 to 2 and 20. So 20 partitions from 0 to 2. Alrighty. And then we said let y1 equal, oops, this is all commentary because I'm going to do different today. Let y1 equal f of x from above. Let y2 equal the tangent line of f of x at x equals 1, I think it was, we figured out would be 2x minus 3, so 2 times x minus 3. Don't forget, times multiplication is explicit. You got to say it. You can't just write 2x, right? All right, and then we're going to say plt dot plot x comma y1 and where is it? plt dot plot x comma y2 and then we did stuff like oh, I don't know, I think we said plt dot xlim from 0 to 2, so it only shows that much on the graph for x, and then we did some labels. Did something like plt dot x label quote x in widgets. So do linear, see if we're sort of like doing a linear programming problem, right? Widgets, okay, and then, whoops, and then comment plt dot x y label y in millions of dollars. And we took a while to get that working, but I figured let's do it this way instead. Okay, you ready? Alright, so we're still going to do the linspace thing, but just this, x equals linspace from 0 to 2 in 20, because we already defined, we already imported numpy, right? So I don't have to do that. Then y1, we're going to still do that y1 equals f of x, and we're still going to do y2 equals 2 times x minus 3. And then we're going to do plot x comma y1, so we don't have to do plt dot because we already imported plotlive.pyplot all of it, right? That makes life easier. But you should know what's coming from what, so that's why I put the commentary there. And plot x comma y2, and let's do the xlim. This is all from pyplot. Xlim from 0 to 2. Actually, I think you have to write it this way. So that's an error. Let me fix it up here. It's just a comment. It won't mess anything up, but let's do it right. And then x label. You know, just copy this. Can I do that? I don't know if this is worth doing it this way, but alright, so copy, and then here, Control V to paste, but get rid of the comment and the PLT, and likewise here, and run it. And there's your graph. Okay, so it's limited to the x values limited from 0 to 2. And we have a tangent line at x equals 1 to f of x, and here's your tangent line to x minus 3, right? See the y-intercept there, and the y-intercept there for x squared minus 2, and it's all very nice. Okay, so that's how I'm going to be graphing, based on step 0, cell that initializes all the imports and stuff. Alright, so that's in function mode, but what about this? Comment. Why is it doing that? I don't want that, I want this. Okay. Okay, so comment step 4b. So graphing an arbitrary window. But what if you want to do parametric mode or polar mode, right? So what about parametric and polar plots? Okay, so whoops. What about parametric and polar plots? All right. So this is what we did last time. We did import numpy as np, and then import matplotlib.pyplot as whatever plt, and then we just said t equals np.arange from 0 to 2 pi. Now pi is coming from numpy, and arange is coming from also numpy. That's interesting. Yeah, I would have to do it this way if I didn't import it in step 0, np dot, right? I think so, but alright, let's keep it simple. And from 0 to 2 pi in 0.05s. So 0, then 0.05, then 0.1, then 0.15, and so forth. So 0.05, like that. And I think that's it. Okay. And then we got it to graph like doing this. plt.plot plot. Okay. Now let's say I want to graph and x of t, y of t, parametrically, right? But what I'm really after is a polar plot, r of theta, right? So let's say r theta is 2 plus 3 sine t, which would be a limit with an inner loop, or cardioid with inner loop, with vertical symmetry. So what I'm going to do is I'm going to graph r cosine of t as your x of t, and r sine of t as your y of t. So what we're doing is this quantity 2 plus 3 times the sine of t times the cosine of t. And again, I'd have to do MP dot, and I don't want to do it that way. This is too complicated. So even here, comma, or that's your x of t, that's your x component, like vector notation, right? Then the same thing, but let's say quantity r of t, which is 2 plus 3 times the sine of t, and then times sine, r of t times sine of t, whoops, is going to be your y component. Okay, so that closes the r, that closes nothing. I didn't close r over here. Wait, hang on. Yeah, I need parentheses here. Okay, so that closes r, that closes the cosine. Okay, so what's messed up here? That messed it up here too. That closes r. That should close r. There you go. And then that closes the sine. That closes the plot. That closes nothing. I don't need it. There you go. That's it. Okay. So that's how we did it last time. But look how easy this is with the step 0 initialization we did. T equals a range again, but I don't have to do np.a range. From 0 to 2 times pi in whatever increments you want, so it's not too choppy, right? That sounds good, okay. And then just plot, instead of plt.plot, that whole mess. I should probably just copy it. I'm just going to copy this. And put it here. There you go. And you should get your cardioid with an inner loop or limit. What did I do? Whoops. Where did I write sine t? What? I wrote sine t somewhere. Oh, where did this come from? Yeah, that was a mistake there, which got propagated here. Control Enter. And your limit with an inner loop. Perfect, I like it. Very nice. Alright, that's it. Done. So, there's setting up your functions and your imports. There's doing numerical derivative. There's doing numerical roots using Newton's method of the numerical derivative. There's a trapezoidal sum using a right sum and left sum, and your list comprehensions and your sum of a sequence and blah blah blah. And there's your function mode graphing, and there's your parametric mode graphing, which you could use to do polar graphing too. And so that's it. Alright, so I think we're done. So thanks for watching, and I hope that's helpful. And there's your calculus, Pythonic Calculus Executive Summary 2017. Enjoy! Bye-bye.